Okay, with
Windows.
about 5 minutes delay, we'll start with our morning session on Monday. And we start with Amnon Besser on the computation of p-adic high pairings.
All right, thank you very much for inviting me. This basically starts, I think, from some work that William did a couple of years ago when they sort of computed p-adic high pairings for elliptic curves, and then I sort of thought that I could do something for hyperelliptic curves, and it turns out to be not too difficult. So we've been thinking yesterday about comparing the two methods in the case of elliptic curves, and sort of I think we're kind of convinced that it somehow should be the same, but we can't quite make the comparison yet. Anyhow, so let's see what's the setup. So I'm going to start with a prime number p, a number field f, a smooth complete curve with good reduction at places above the prime p, and J is going to be the Jacobian of C, and you'll see that there's some additional data involved. I'll introduce them, and then there's a p-adic high pairing going from, so it's a symmetric bilinear pairing between the f points of the Jacobian and QP. And as I said, Mesos starting date, I don't know, so the paper is in 2006, but this was done in 2004, but 2003, so have a computation in the case of elliptic curves, so we'll GC1, and the goal is to compute in general, actually I should say, well, compute for hyperelliptic curves in general.
Is there a definition for the undividing and dual in general?
Yeah, there are more. Yeah, of course, there are more general. There are more general definitions. I mean, that's all I didn't want to touch on that. There's sort of many definitions of p-adic high pairings. I think when I spoke in Budapest, I sort of surveyed some of them, and I guess the most general definition is for Galois representations, with crystalline at p. I guess even semi-stable at p, and that was given by Nekovar. And one of the things I showed was that this was the same as this Coleman-Gross definition for Jacobians of curves. So I mean, I'm not gonna. And then I think Coleman himself showed that this definition was the same as, at least in some cases. Well, there was a previous definition for abelian varieties, I guess, by Schneider. And that's actually, I mean, that sort of, you have to specialize the data in a certain way, and then you get that. And then that I think Coleman proved. So, as far as I know, all the p-adic high pairings are essentially the same. So just pick one and you implement that. So, so this is work of Coleman and Gross from '85, and so again, same assumptions. C over F, smooth, complete, good reduction above F. Now, here's some additional data. You need an Idel-class character. So IF are Idels of F, and you take the character of IF mod F star into QP. Well, continuous character, I guess. And now the high pairing is a sum of local high pairings. Actually, what will happen is that the local high pairings are just on divisors, and the sum of all of them actually factors of the Jacobian. We'll see how that happens. Well, okay, let's start with the case which is, well, for me, less interesting. That's sort of the case which is like the classical case. You look at the local term for places not dividing P, and what are the assumptions? And I'm sure I forgot to write something about this. So you take a So actually, I should have said that. I mean, everything here happens in the non-Archimedean case, so there's no sort of Archimedean contribution. So now I'm going to specialize. So everything specializes to now to a local field situation. So you now take a curve over a local field, which is this completion of f at b, and you look at two degree zero divisors with C, and now, what I probably forgot to mention is that the support should be disjoint. Now, to define this, I'm going to go back to this at the end of the lecture because although it's in some sense less, at least for me, less interesting, one has to do something about it. So I'll try. And it's also the thing that I've not done very carefully. So just sketch this. So what you have to do is you have to take a regular model for C, and so over the ring of integers of K. And now what you do is you make two extensions of Y and Z to rational divisors. I'll explain what you do. Rational divisors, now one of which at least has to have zero intersection with all components of the special fiber. So you think you have a rational section, like you take one point out of the points defining y, say, and you sort of extend that to a section. Now that could have, I mean, that of course will intersect on the special fiber, assuming that the special fiber is by reduction, that will intersect just one of the components. What you want to do then is to modify that by adding certain components of the special fiber in such a way that it actually does not intersect any of the components of the special fiber, and then you just define so the local contribution Y and Z to be the local contribution in angle brackets times the value of the V components of chi evaluated at the uniformizer of the uniformizer pi V at V, and this bracketed thing is just now the intersection on this regular model of these two extensions. So,
sorry, what was chi V again?
So chi was this ideal class character. You decompose it into a product of local terms, and then the local term at V is now something on the completion of, completion of f at V, and you just evaluate it on uniformizer. So now what about the local heights above P? And this is like this p-adic version of hierarchical theory that involves, starts involving Coulomb integration theory. So again, you just sort of work locally. So now you take K to be a finite extension of QP. C is now smooth complete, and maybe, well, I should say that somehow the assumption of good reduction was made by Coleman and Gross, because that's where the Coleman integration theory used to work. Now there are extensions of Coleman integration theory that work in general, but they're not quite computable. I think if you understand the reduction sufficiently well, you could probably do computations. But so while you could define this for in the bad reduction case, probably for computations you still want to assume good reduction. So now you need additional auxiliary data. Now notice this is sort of already on the local level, so that means that for every completion above P, you're going to have to make a choice of this auxiliary data, and this is the choice of a complementary subspace W to the holomorphic forms inside the first de Rham homology of C of K. And then I should say that for some of the in many of the works, one just sort of takes, for example, make an assumption of an ordinary reduction, and then one just takes the unit root subspace. So that's sort of somehow there's a canonical choice of this complementary subspace in certain cases. Okay, now what do I have to do? So I have to sort of recall for you for a second what is the Jacobian. So the Jacobian has, I mean, the L for a finite extension of, well, for any extension actually of K, the L points of J are all the zero divisors of C scalar extended to L, and then you just divide by the principal divisors. So that's and what you now of course this is false. You actually the local term is not on the Jacobian. It's just on it's really just on zero divisors. As I said, it's the global term factors for Jacobian. So you need two inputs for that. One is the notion of the universal vectorial extension of J and its logarithm, and the other one is Coleman integration theory.
Excuse me, are you assuming a rational point on C, or a degree one? I mean,
well, this is sort of a zero divisor, so it's sort of right. It doesn't have to actually consist of rational points, but somehow it's sort of it's an orbit. It's invariant.
Well, it has to be Galois stable.
Yeah, it has to be Galois stable. Right?
Yeah, but a divisor class, right? The divisor class doesn't have to contain a rational divisor.
I think he's complaining about your description of J of L, which isn't, I mean, if C doesn't have a...
You want to assume there's a rational one.
Or degree one, yeah.
Not,
Really want to define
Rational degree one.
JFK bar gal.
Well, I mean, what will
Invariance.
well, I mean, here, I guess with divisors, zero divisors are sort of, the divisors on C tend to are spanned by closed form rather than rational forms, right? And I think
but there's still a problem that not every element of not every point on the Jacobian is represented by a divisor that's rational over
Degree zero.
over L. It could be just a divisor class that's Galois stable. An element of
okay.
You have to take like JFK bar and then take the Galois invariance.
Okay.
And then your definition would be right.
Most of the time when you're computing, you have at least you're going to have at least a rational.
As long as you're
Yeah, I mean, that's not
You're
very
usually going to have a rational point.
Yeah, no, I don't think that I mean that probably doesn't bother me because I always just work with some kind.
even if you have a local point.
Yeah,
you
can make K larger.
Yeah, I could just make I should just make my field larger. Okay, now so here's the universal vectorial extension. So what you do, you look. So here's CL is C tensor L. So you look at all forms of the third kind, which are, so this is a subspace of all the forms of the meromorphic forms on C. C extended to L. Now third kind, for those who don't know, means that it has simple poles and all the residues are actually integral. So inside of the space of forms of the third kind, there's the space of logarithmic form, which just means that you take a rational function and you take its d-log. So certainly that falls in this space.
So C sub L is just C extended to L.
Yeah, it's C squared.
And when you say that all simple poles and residues in Z, you're looking at C as a curve over some. Like, is it globally? Is that a statement about the points globally, or like are we assuming C is defined over the number field, and then we're?
Well, no, I mean this is completely local. So I just want.
Residues are not the poles.
Oh, I see.
Yeah, so it was simple poles, but the residues actually
So
have
the
to
poles,
be.
not the poles, the red.
Okay, so so then so you have these logarithmic forms, and now there's the following nice description. So I could now you see that there's a residue, which is a residue map from TL to divisors on CL, where you just sort of take like the sum of points with the residues. So there's a map like that, and one can show easily, I guess, by Riemann-Roch that it's surjective. And the kernel is, of course, just holomorphic differentials, because if the residue divisor, if it only has simple poles and the residue divisor is 0, that means that it's actually holomorphic. So there's this short exact sequence. And now if I quotient out by the logarithmic forms, what I get, of course, you see the residue divisor of the d log of f is just the divisor of f. Right? So what I really get is I get the following thing. You get holomorphic differential forms, and then you go to this quotient, which I'll call G of L, and then the quotient maps to the L values of the Jacobian. So now you take. So now you can show that this is actually an algebraic description. So I mean this is actually a map of group schemes. So it's the L points of a universal vectorial extension, where here you have a vector group, omega 1c, and then it goes to G and then to G. And now if you look at the tangent spaces, well, at 0, then of course omega 1 is just H10. The tangent space to the Jacobian is well known to be H01. And not surprisingly, the tangent space to G is just the full Durand commodel, and you should get this short exact. Now, there's a logarithm for all commutative group schemes over a p-adic field, where you so somehow the idea is that you, of course, you can invert the exponential map locally, and then if you have any point, you just sort of multiply by sufficiently large, well, it has to be, I guess, sufficiently divisible integer to put it in this neighborhood where the exponential is invertible. Then you take the logarithm, which is the inverse of the exponential, and then you divide by n again. So there's a logarithm map from the k points of G to the tangent space, and of course on the vector part, it's just the identity. So that's the first component of making the definition of the height pairing. Now, and another thing I need to do is I need to consider the choice of a branch of the logarithm and a trace. So what one has is, remember that V is now a place dividing P. And so if you look at, and you can show that the chi V from FV star, so the star came out at the wrong place, factors as follows. There's a logarithm, so it's so it's a map that well, how does one say it? So it converts multiplication to addition, locally defined by near 1 by the usual power series. So there's some choice here. Basically, just need to choose a log for some uniformizer, and then so that maps from FV star to FV, and then in fact, and then there's a trace map from FV to QP, and so one makes one can factor into this like that. And so now I have to say something about Kalman integration. Now the idea is, I guess, to say as possible about Kalman integration, because that will be further exposed in the next lecture. So for now, I'll just say what the base. Well, this sort of setup that we need here. You take meromorphic differentials on C, and that and in Kalman integration converts that to a function which is on k bar points of C into k bar, and it depends. I mean, this setup actually, the function depends on this choice of the logarithm, branch of the logarithm, and maybe I should, of course, I should just say two more things. One is there's some Galois equivariance condition here, so the f omega is Galois equivariant, and the other thing I should say is that this is unique up to a constant, so there's some constant of integration which you cannot fix. So now let's see. Now now I'll explain how the height is defined. So first of all, one notices the following. So I look at tk. You know, these are the sort of logarithmic, forms of the third kind, and I say, well, for my given divisor y, I can find a unique form of the third kind, omega y, that satisfies the following conditions. First of all, its residue is y, so it has the poles with the residues at the appropriate places. And now this, remember, is not uniquely defined because there's a choice of you can add a holomorphic form and nothing changes. So the other condition is, remember, we have this auxiliary space W, so I have to make the assumption that the log of omega y sits in W. And you can, if you think about it for a moment, the point is that omega is complementary to the space of holomorphic forms, and log on a holomorphic form is just the holomorphic form itself. Therefore, this space actually removes the indeterminacy by the holomorphic form. So that really determines omega y UB3. And now you just set the local component for the height in y and z, that's going to be the trace of the integral against z of omega y. So I should say, just in one word, what does this mean? So omega y has this Coleman integral, so some function. And remember that this is only defined on up to a constant, but I can sort of evaluate this function on a divisor, right? So if I want to evaluate it on the divisor sum nixi, I just sum nifxi, and if the divisor is a zero divisor, a constant of integration doesn't matter because it's going to fall off when you sum over all the points. And so that's the definition of the Coleman gross height pairing. Now I should say that there's one observes the following point, that in both definitions, so both for primes dividing p and for primes not dividing p, there's the following property. If I take one of the divisors to be principal divisor, so HV of the divisor of f against z comes out to be the local component chi v of f of z. Okay, so therefore you see, if I now sum all of these, I'm going to get the sum of the chi v's of fz, but this is an ideal class character. So if I sum everything, it's going to die on things from f star, and so that shows that the h actually factors by the Jacobian. So that's why the global thing actually factors by the Jacobian. Okay, now maybe I should go back. Now you see that this sort of definition has two components. The first component is this logarithm, and the second component is the Coleman integration. Now, Coleman integration, we now, at least under some conditions, we know how to do. So the more difficult thing, at least to start with, is this logarithm, because the logarithm requires you, in some sense, to understand not only the Jacobian, but actually some vectorial extension of the Jacobian, and so it's not very easy to understand. So one needs a different description of this logarithm, and unfortunately, I actually found one a couple of years ago, and for that I need to explain something which is sort of a very nice linear algebra trick that somehow makes everything very, very easy. So there's a notion of what I call the double index, and I'll describe this. This sort of has it works in two different contexts, and the easiest one to explain is just sort of a formal algebraic context. So what you do is you just look at two differential forms, omega and eta, and these are just sort of meromorphic differential forms in the neighborhood of zero. So you just take a Laurent series in Z, finite Laurent series, so finite number of pole, only a finite order of pole times dz, and then now what you want is you want to make a definition of a notion of what is the residue at zero of f omega times e. Okay, so you have an integral of omega. You can sort of, on that level, you can sort of integrate completely formally. You multiply by this form eta, and then you want to say what is the residue of zero, this sort of one form. And sort of to see what the problem is, that just observe that, let's say that omega actually contains a component which is dz over z, right? Which may well have. And then if I integrate it again formally, and Coleman integration would sort of somehow locally look completely formal, you're going to get in f omega something like a naught log z, because the integral of dz over z sort of formally is log z. So, and then you see that to make a notion like that, you're going to have to say what is the residue at zero of something like log z dz over z. So it's something kind of weird. Now, so one thing we could start observing is that well, many times there's no problem, because of course if there's no log z here in omega, then I have no problem. But also if so that means that omega doesn't have a component dz over z, so there's no residue. But also if eta has no residue, I'm still okay, because you see, you sort of formally would like to have that the residue of f omega times eta plus f eta times omega should be zero. because it's like the residue of d of f omega times f eta, so somehow formally it should be 0. So in the second case, let's say that eta did not have a residue. I could just sort of define the residue of f omega times eta to be minus the residue of f eta times omega. So that's somehow still reasonable, but you're still faced with this situation of log z dz over z, where you kind of don't know immediately what to do. And the solution is to simply take this as a formal expression depending on both f omega and f eta. And now this is just a completely trivial exercise in linear algebra. Let's say that I look at f omega and f eta, and I want to make some definition like this, and I insist that it has the following properties. It should be bilinear, it should be antisymmetric, and it should sort of be the same as what we had before when it was defined. So either the residue of f omega times eta or minus the residue of f eta times omega when this actually makes sense. So now, just to see why that works, you see that because it's antisymmetric, that means that the pairing of log z and log z should be 0. And that's the whole trick, because now you can sort of decompose any function like that into a log something times a log z plus things where there's no log. So the only complicated case is log against the log, and that's taken care of by the antisymmetry. So it's completely trivial algebraic observation, but it seems to have very nice application. So first first observation is the following. Of course, since the integral is only defined up to a constant, so one observes that if I change f omega by a constant, I'm going to get the same index. Oops, yeah, we should cancel the x. This is no x. It's no x here, but it's you just get this constant times the residue of eta. Okay, so that in particular shows you that although I sort of said this was somehow a replacement for the residue of f omega times eta, it's not. It's not really that. Well, okay, you can have the same sort of behavior if I modify f eta by a constant, and the actual integral on both variables really matters. So it's really a function of both f omega and f eta. Now what I do is I sort of have a global index. Now here the idea is, well, I should probably have added a few more words. So let's say that now omega and eta are one forms on a curve. I could meromorphic one forms on a curve. I could sort of do the following thing. I just sort of go over all points of the curves. Let's just say that I'm now over algebraically close to it, so I have no problems with that. And then I do the same procedure just by choosing a local variable. I compute this local index at h point x, and then I sum over all points. And then that I call the global index of f omega and f eta. And at that point, I want to choose these functions, f omega and f eta, to be common integrals. And then one first of all observes that this thing actually only depends now on omega and eta. It doesn't depend on the choice of the constant of integration. And the reason for that is it just comes from this previous equation and the residue theorem. You see, if I modify f omega by a constant, then all of the indices are going to change by this constant times the residue of omega, of eta. But then if I sum over all the points, I use the residue theorem, and everything. The sum is 0. So that means that it only depends on omega and eta. And now another important observation is that I can change some of indices on points by an index on an angle. So if I have like one small disk and I have a bunch of points where I want to compute the indices on these points, I can just replace that by doing a similar construction on an alias that surround these points. So that's how I'm going to appear in the computations. Now, here's the thing that starts sort of to allow us to compute the log. So here's a theorem. Actually, all of these are now fairly easy somehow, so it's not that difficult. So one makes a projection in the following way. So I take a normomorphic form omega on C, and I define psi of omega to be the round class on C in the following way. So you look where the round cohomology has a basis which consists of forms of the second kind, so normomorphic forms but with no residues. And I do the following thing. I take the global index of omega and alpha, where alpha is one such form of the second kind, and I want to insist that this is the same as psi omega car product with the class of alpha. And that defines this uniquely. Pairing is car product pairing is non-degenerate, so there's a definition like that. And now, so there are two things that one observes here. First, it so happens that this psi extends the logarithm. So if I took a form that only had logarithmic, only had simple poles with integral residues, this psi is going to be the same as the log that we had before. That's the first thing. And the second thing, there's a formula that says that if I take any two forms, omega and eta, the global index of omega and eta is the same as the car product of psi of omega and psi eta. And this is a generalization, and all of this is somehow inspired by by the paper of Coleman on reciprocity laws on curves, but it's more general. And actually, I guess it's both more general and the proofs are simpler eventually. Now, one needs at some point to say that this sort of works in greater than generality, not just in a sort of an algebraic context, but in a rigid context. So, so you could sort of replace indices on points by indices on annuli, as I said before, and one discovers that there's a projection from forms on some open U in C to the round cohomology of C, and one discovers that this is the unique Frobenius equivariant splitting of the restriction mapping cohomology. And now the nice thing to observe is that once you have this projection formula, that means that the log is the same as this psi. For doing this psi, you just need local indices, which are, very easy to compute. As I said, it's just sort of trivial linear algebra, and common integrals. So the whole point of that is that if you know how to do common integrals, then you know how to compute the log. Okay, now here are a few remarks. First remark, which is really crucial. Sorry. This is actually a remark already. So this is a crucial remark. If I compute the global pairing of omega and alpha is of the second kind, I only really need to compute the Coleman integral of alpha. And the reason is, remember that the constant of integration multiplies the residue of the other form. So if I change omega by a constant, I pick this constant times the residue of alpha at a particular point, but alpha is of the second kind, it has no residue. So I really don't care what is the constant of integration for omega. And that means that I don't have to globally integrate omega to do a common integral, I just need to locally integrate that. And locally integrating is no problem. You just sort of integrate as you wish. So, okay, now what do I need to say about computation of common integrals? So, so this was, the sort of the first implementation in Magma, which was done by Igor Gutnik, who's was a master student of mine, and this is like this. I guess Kieran calls this an orphan because nobody ever checked that it actually works. So, which is of course
I haven't checked it.
Yeah, which is sort of totally my fault. I mean, so guy submitted his thesis and he gave me the code, and then I just put it aside. It's been lying there, and then the world. Now the implementations on Sage, and I'm quite sure that they are actually better than what we did anyhow. Okay, so now the difficulty with this, both with the implementation by my student and with the implementation, I mean, I don't know what are the credits. So I mean, I guess it's you and then Robert Bradshaw and then.
Well, so I sort of proposed this as a project at the Arizona Winter School, and Robert basically did it.
Okay, so
And that's Robert, by the way.
And Robert is
right there.
Is going to be.
Oh, hi.
He and I are going to be sharing the next following hours, so you'll get to.
Okay, anyhow, so yeah, so basically, so the drawback of this is that it only works with sort of residual, well.
You should first say that we're talking about hyperelliptic curves.
Yeah, right. So it doesn't say at any point here that this, because this uses Kieran's algorithm, well, essentially some slight extension of Kieran's algorithm for point counting. So we just sort of compute explicitly the Monsky-Washington cohomology. And it's an extension only in the sense that you don't just need to know what for a given form what its cohomology class is, but you also need to know that it's given as it's given as a combination of a basis element cohomology plus the d of a function. You need to remember what this function is. So that's the only extension. It's like extended. It's exactly like the extended GCD compared with the GCD.
Yeah, we should see details.
Yeah.
Section of next time.
Yeah. So, but at least so far, it's only implemented in the case of forms. So, on this hyperelliptic curve with residually Weierstrass singularities, which means that all the singularities have to reduce to Weierstrass points. Right? And the reason for that is that the Kieran's algorithm works when you just sort of compute the cohomology of like a rigid subspace, which is the one where you get by removing all of these residually Weierstrass points. So that means that that you have to assume that the forms are there to be able to do that. Now, for these applications in p-adic pairings, you need more. And then so I mean, so either you have to have a more general reduction algorithm so that you can handle more general forms, and that's what I'm going to do is I'm just going to somehow use some tricks to avoid it. So eventually what happens is that you only need, well, in the sense of these algorithms, you just need to compute Coleman integrals for these, for the forms that you already know how to do. You already know how to do this. Yeah. So that's what I said.
And you know how to do those tricks now?
What?
You know those tricks now? So you're saying that you do have tricks that allow you to reduce this case?
I have these tricks, and this will suffice for that. Of course, I mean, this will also work for just computing Coleman integrals in this case, but I mean, I don't know if they will work for iterated Coleman integrals. So some tricks, and one thing I'm not sure about, I haven't sort of thought about it very carefully, is whether these tricks are actually better than doing more general reduction if you know how to do it. So there's sort of a lot of, I mean, there's some questions of what's the best way to do more general Coleman integrals. Okay, I guess I'm going to in here. Okay, so now let me sort of explain the algorithm at P. So what does one do? So first of all, you see that really I only need to consider antisymmetric divisors. So again, I mean, I'm on a hyperelliptic curve. Antisymmetric means with respect to the hyperelliptic evolution. And the reason is that otherwise the divisors split into antisymmetric and antisymmetric. Symmetric ones sort of come from P1. You basically know what to do with P1. And so really you see that only you have to consider antisymmetric ones. So you start with antisymmetric y's and z. And so here's the first step. Here I sort of, this is again, sort of reference to the next talk, we have to, quote unquote, compute Coleman integrals for a basis of the round cohomology. So hyperelliptic curve is a very standard basic, something like x to the I dx over y. And you just need to sort of pick out a basis like that and compute the Coleman integral for each one of these elements, and you need to compute the cup product sort of matrix for all of these forms. And when I say compute Coleman integrals, and you'll see more in the next talk, basically there's sort of two steps. One which can be sort of preparatory, where you, for example, carry out Kieran's algorithm and maybe add some more information, and this you have to do once, and then you can say that you've computed a Coleman integral, and then if you want to evaluate it at a given point, then you have to do something more, which is sort of a little bit more than an evaluation. So you have to do something, but at least there's some preparatory things that you can do independent of a choice of a form. So that's what I mean by computing the Coleman integral. And a consequence of that is that you can now compute this psi. And the reason for that is what I explained before, that if I take the global index of a general form and a form of the second kind, I only need to do Coleman integrals for the form of the second kind, and I don't need to do this for the other form. So once I have computed these Coleman integrals for this basis, I can just compute my psi. In other words, I can compute the log of the for this universal vectorial extension, and so and it turns out that really no further Coleman integration is required, in the sense that I've already done all of this once I done this for this basis, and in this case there will be extra Coleman integrals, but they're going to be simpler.
So is this cup product, is computing the cup product matrix a bunch of local index terms?
Yeah. Well, this is sort of, I mean, this is easier than local index, right?
Oh,
so you just use, so here there's no Coleman integration involved at all, because both forms are the same.
Right, both forms are the second kind.
Yeah.
Okay.
So this is just, I guess.
So it's just you formally integrate.
Yeah. I mean, I don't know. I always say that this is a formula due to Serre, but I'm not sure that I've ever seen a reference. So there's this thing where you cup product by sort of summing up the residues of the integral of one form times the other form. I think I once seen that this is due to Serre, but I don't think I've ever seen a reference. Okay.
It's probably older than that.
Find out.
What?
There is another thing here now. We can.
I know. Yeah, we can ask.
It might be older than that. I think
It might.
that might go back to their Riemann surfaces.
Yeah. Well, I guess in Riemann, yeah, probably. Yeah. Analysis you can do much more as usual. Okay. So now here's the second step. So the second step is to compute this omega y, which I remind you is this form such that its residue divisor is my given divisor, and such that it has the property that its log sits in my W. Now I should say that here I'm going to sort of pretend that I'm kind of like working over a sufficiently high extension over the algebraic closure, so I'm going to really think about my divisor as being a sum of points, and of course that's computationally not very good, but I mean, just once you have the formula, I guess as usual, you can see that eventually you don't really need to extend scalars ever beyond the original field. So let's see. So you want to take So what you do is you first pick out any form with a residue divisor y, and again, this is an anti-symmetric divisor. I just sort of like pick 2 points, and I just need to find a form whose residue divisor is p plus minus p, and then I compute its log, so I know how to compute it as a psi. And then, if I know what this psi is, I know what is the holomorphic form omega minus omega y, because then this psi lands somewhere, and I just need to decompose the psi of omega as something in W and something holomorphic. And this holomorphic thing is exactly going to be the difference between omega and omega y. And since I know how to compute the integral of the holomorphic form, because that's part of the basis of the rank homology, which I've already computed, I'm now basically reduced to computing the integral against the divisor z of my omega. So I'm done with that, and now here comes the most difficult part, which will actually, in a sense, will give you a hint on how one computes Coleman integrals in general. It's sort of like in a sense, it's sort of a baby case of that, because what happens is that you sort of need to do Kieran's algorithm to compute Coleman integrals. Now here we've sort of started with the curve, and we've taken out these residual Weierstrass points. Now you sort of cover the whole cohomology of the curve, and there you have to do the complicated part. Now if I remove extra points, what I sort of get is just sort of like a Tate extension of that. So every additional point, you just need to do something which is one-dimensional, plus the sort of Frobenius just acts by P somehow. So it's the same procedure in a sense, but it's much easier. So let's see. So what I want to do then is, so as I said, I'm working on an antisymmetric divisor, and I can just split it into points. So I'm just going to consider the case of how to compute the integral between minus p and p of omega. So now I can choose my f omega to be antisymmetric itself. So that means that the integral is just, so if f is the integral of omega, I just get 2 times f of p. So that's all I have to do. And as I said, I'm going to mimic the procedure that showed up in the algorithms of Algorithmic and Bradshaw in this case. So what you do is, so your phi is going to be this lift of Frobenius, and I just look at eta, which is phi omega minus p omega. That's the Tate thing. So phi now just acts sort of formally, essentially, on the cohomology by p. So now this eta is quote unquote of the second kind. In other words, you see, basically the residue, the corresponding residue for phi of omega is just p times the residue of omega. But it's not at the same point. But these 2 points where phi of omega and omega have a residue are at the same residue disk. So if I sort of remove all of this disk, I'm kind of the residue around that disk is going to be 0. So it's not quite of the second kind, but it's almost like that.
Right, isn't it actually that there are p different points where phi omega has a pole, and each one of them has the same residue as omega, and that's how it cancels out? Say omega does omega have 1 pole in this disk? Right, I think because phi, on these disks, phi splits, it has the same effect, but I think what's literally happening is that you have p different points, because phi is a p-to-1 map.
Yeah, I guess, yeah.
So it's
yeah,
star, right? So you have p different points, and the residues together cancel p times the residue of omega.
Yeah, you're right. Yeah.
So the sum of all the residues in the disk is still 0.
I guess I already thought about this sort of residual. Yeah, of course.
Yeah.
But anyway,
it has that effect.
Okay. So then, now that's sort of the critical step. So, and then you'll sort of, I guess you'll see this better in Kieran's talk. What happens is that you get the following formula. So this is like, now this relation that eta is phi omega minus p omega lifts, that's the whole idea of Coleman integration, that actually lifts the integral. And the effect of phi, and this phi is, I should say, is the sort of semi-linear Frobenius. So it has this effect of functions where you first sort of apply sigma, which is the Frobenius on the Frobenius substitution on the field. You apply sigma minus 1, and then you apply p to p, and then you apply f, and then you apply sigma. So there's something that goes on here, and then p times fp, that corresponds to p omega, and that's going to be 1/2 of the integral between minus p of p of eta. And so that means that now what happens, again, would make more sense after Kieran's talk. Or is it Robert Stock? I don't know.
Yeah, well, after, yeah, we're splitting the time.
Okay, yeah. So I mean, there's going to be some equation here, and if I know the right-hand side, then I'm going to be able to solve it. So try to skip that so I don't steal the punchline from the other talk. So what I need to do is I need to compute the integral from minus p to p of eta. And you see here, it sort of like looks like I've somehow done nothing because I've only replaced the integral from minus p to p of omega with the integral from minus p to p of eta. But the point is that this integral of eta is sort of the second kind. So in that sense, we're slightly better. And why is that? Well, now I'm going to take a form whose residue divisor is p plus minus p. And now you see the right-hand side I can rewrite as the sum of the residues of mu times the integral of eta. Because, I mean, well, just that this has sort of one pole at the point P, and one simple pole at the point P with residue 1. So when I'm being multiplied by integral of eta, I'm going to pick up the value of the integral of eta at mu. And then for minus p, I'm going to pick up minus the value at minus p.
Does this
So-
maybe also have a pole at like infinity or something? Or does it not need it?
Well, no, but what here I'm just sort of looking at the sum of the singular points of mu. And I guess I should say p minus minus p. P minus. So that's so anyhow, so I only sum up against the singular points of mu at that point. But then, I mean, but now the residue of mu times the integral of eta in that case is just like the local index. Now my projection formula tells me, or not, yeah, projection theorem, I guess, tells me that if I sum up over all points the local indices, I'm going to get the cup product of the projections. Now I know how to compute the projections, and I know how to compute the cup product because I've already done that. And so consequently, I can just replace this sum, my mod something which I know, which is the cup product of the projections of eta and mu. I get something which is the sum of, plus or minus, I guess, the residues of eta times the integral of mu.
Wait, can I ask on the previous
Yeah.
slide, when you talk about the residue divisor, do you mean you take a form that has simple poles at those points, and the coefficients in those points are
The residues.
residues?
Okay. So this should be with p minus minus. Yes. Oh, okay.
So it's not really a divisor in the sense that the coefficients are not integers.
Well, I mean, in this case, in general, it's
I mean,
not.
in general,
In general, it's not. Yeah.
Yeah.
So it's a divisor with coefficients.
So is it allowed to have other poles with residue 0 or
I guess, yeah, I think in that case, I'm fine. I guess I'm fine with well, I mean, I think, yeah, well, maybe I should assume that I can actually arrange that because, as I said, and so I don't remember, but I mean, it's easy to write down something that only has this sort of two poles. So then you just get the sum. So then up to knowing something like that, you just get now the sum of the residues of eta times the integral of mu. And now you sum over the singularities of eta. Now here, the point is that after doing all of these manipulations, somehow this is better because eta now is of the second kind. So the integral of mu, I only need to compute sort of locally and not as a common integral. It's again the same trick. So you sort of like do many manipulations, but in the end you end up with something where you sort of have to break down this problem to play around with various forms, and all of the time they have singularities which are not residually Weierstrass, so you cannot do a common integral for them. But somehow if you play around with this sufficiently, you end up with something where you don't have to do a common integral, just a local integral.
And somehow this is okay even though the of second kind is in quotes.
Right, because
it's not actually second kind, but the residues add up to 0 inside this residue.
Right, that's because I can replace, that's what I said, I can replace local indices on points and local indices on an annulus.
Okay,
Right?
great.
And that's why, I mean, that's why it works. And the drawback of that is that, and that's where sort of like, I guess, the computational difficulty would come up. Eta, remember, was this, what was Eta? Eta was this phi omega minus p omega. So even if omega was just sort of had some very mild singularities, this phi is only defined on sort of the complement of the residually varched response. And it actually, so once I look at this eta, it actually has essential singularities at the disk of the varched response. And so what it means is that now, well, that amounts to sort of doing a computation of a residue where one of the forms has essential singularity. So that means that you really have to sort of sum up enough, right? So you have one form which is, say, even holomorphic, and another one which has an essential singularity. So if I want to compute the residue, I have to sort of pair up many terms. And so some with positive sort of local, one with positive uniformizer, and one with negative ones. And I mean, eventually, because there's some over-convergence going on, that's going to, after enough terms, you're going to get a good approximation for what you want. But that will require taking many terms for this. So that's why it's going to be a little bit difficult. Okay, now I just want to go over. I guess I started maybe 5 minutes late, so I'll just try to go quickly on the other part, which is sort of the part that I didn't want to do. So, of course, my main interest is common integration, so I sort of wanted to do the local height of P, but then I was hoping that I could also, so I'll find that somebody had already done the part of the local heights away from P, and it makes sense because that's also the thing that we would do for the classical height pairing, and I searched the internet, I couldn't find anything, so if somebody knows how to do this, that would be nice. But anyhow, so I cooked up something, and I think it works. So the idea is roughly as follows. So what you do is, remember, this YZV is this, so you extend your divisors to the regular model in such a way that they're going to intersect all the component of the special fiber with intersection 0, and then you just intercept them. So the difficulty with that is that if you're in a bad reduction situation, to really do this, you sort of need to understand completely the reduction. At least naively, you'd have to understand completely the reduction type of your curve, and that could be quite difficult. Now, the idea that I have, again, sort of looks like it works, but I haven't checked this in any detail, is the following. So let's just sort of forget about all of these complications and just sort of take naive intersections. So I'm just going to like project on the x-coordinate and see the difference between the x-coordinates. Again, maybe I extend scalars or something. Think a little bit about how to do this. So that's not going to be the same thing, but it's sort of going to be close, and the difference is somehow measured by the complication of the reduction of the singular fiber, and by the degree of the divisor somehow. So that's so you get some sort of bound which hopefully can make explicit. And then now the nice thing about hyperelliptic curves is that due to the fact that I guess they're used in cryptography, people know how to compute with them. So what I can do is I can start with my y, and I can take 2 to the ny, and I can rewrite this as y prime plus f with y prime of some small degree. So this is like these reduced representations for things. And I can do this effectively. And then you see that what I get is, so here everything is bilinear. So 2 to the n of the local intersection is y prime, is the local intersection of y prime and z, plus the valuation, that's the thing that I mentioned at the start, but plus the valuation of this f of z. And this is approximated by the naive intersection plus the, well, it should be v of f of z. And then I divide back by 2 to the n, and I get something like that. And yeah, so So now the point is, you see that this approximation becomes better and better because I'm dividing by a high power of 2. And because I know that, again, the denominators of the intersection are bounded, again, by understanding the complication of the singular fiber, I should be okay for a sufficiently high n. And just sort of to show you that this is somehow reasonable to do, just observe that if I take 2y, I can write this as y1 plus f1. If I take 4y, then it's 2y1 plus f1 squared, and so it's y2 plus the divisor of f2 plus divisor of f1 squared. And then 2 to the ny, I can then write in this way. And so basically my approximations become 2 to the minus n naive intersection plus the sum of the valuation of the fiz over 2 to di. So, I mean, it's quite clear that you can actually do this I guess, in a numerically stable way. And now, and if you actually want to get a probable height, that's sort of the issue of where to stop. So how big n should be. And that's the final slide. There's some work of Kaus that basically tells you what, sort of not very surprising, the complication of the reduction is controlled by the valuation of the discriminant. And I mean, you have to take this discriminant in the right way, but basically that's what it tells you. And so you can sort of, by knowing the valuation of the discriminant, you can probably tell how far you need to go. And for first implementation, I just suggest to take n equals 100, and then I think you're safe by any count. So yeah, so that's the rough sketch of the algorithm. Thanks.
Any questions?
I have a question. So in the elliptic curve case, so you don't actually take a sum over local heights when you're using this nasal tape method. And it somehow seems to be because if you look at the class group, then you push all the stuff happening over other primes into the p place, and that's why you get this denominator. So is there I mean, when you do the sum of the local heights, you have to figure out which ones are actually there. And it sounds like you end up having to like factor an integer at some point to work out which primes are playing. Does that come up anywhere in the computation, or how do you figure out which heights to look at?
Well, I mean, I think what you have to basically do, again, I mean, sort of, I haven't figured out quite the details on that particular part, but I guess what you might, I mean, there's going to be what's the word, the resultant for so there's going to be one function that will tell you what are the x coordinates for one divisor, another function telling you what are the x coordinates for the other divisor, and then you take the resultant of that, and that tells you where at what points there's any intersection between the two divisors, and then may have to and then possibly may have to factor the resultant. That might be necessary. Although, I mean, I don't know. Maybe
you also have to know where the bad places are, which so you have to factor some discriminant in the beginning.
There isn't the kind of thing where you could just pretend. I mean, factor partially.
I don't know. I
pretend that the factors are prime.
You may or may not be able to do that. I haven't thought of it.
Well, my experience with the elliptic curve case is that if you try to do it explicitly with that formula, you run into a big problem there because these denominators get very big very quickly, and so, but somehow the theory lets you avoid that by pushing all into that single denominator, and I'm curious whether something like that.
I see. So instead of having local things, you have this global thing, which is the denominator, and that lets you move everything into the prime p, which is where you're going to do your analytic calculation.
Yeah.
Well, I mean, I have to admit I haven't quite thought about this particular problems. I mean, it may or may not be necessary to do factorizations.
So another question I have is, so there's this, so again in the elliptic curve case, there's this result of Woodruff, which says that there's some nice finite index subgroup, which if your point P is in this finite index subgroup of the modular Vega group, then you don't have to worry about all the bad reduction at all. Just the contributions there are trivial. And is that what you were doing on the last slide or two there? Was it somehow trying to like take some multiple of that divisor is pushing you into a nice subgroup where you can...
Well, not
you
quite.
need primes other than 2 to do that.
Yeah, not
You
quite.
have
I mean,
multiples of them.
see, with the problem, what's the problem? The problem is that you sort of take 2 divisors. If they intersect, if you're at a prime of bad reduction, and these 2 divisors intersect at a singular point, then the intersection becomes complicated. And at least in theory, maybe if the residue field is sufficiently high, you could sort of expect that if you multiply one of these divisors by something, and of course, I mean, when you multiply, you're doing some sort of reduction. So naively, well, you would expect that somehow, just by doing some things like that, doing some modifications, you're easily going to get into a situation where your divisors do not intersect at bad points at all, so there's not going to be, or maybe do not intersect at all, so there won't be any problem at all computing the local terms. But I mean, again, it's sort of a question of how difficult something like that is to prove. So this is actually an alternative to doing that, which is like in a sense like the definition of the Tate canonical height, which should work without knowing that, but. Again, yeah, there may well be other tricks for you. Right?
Any other questions?
Can I make an announcement? So it's more of a request. If speakers who are using computer slides